Ernesto. Hello, good afternoon. As I've been introduced, my name is Ernesto Fernandez, and I'm going to give you a few methods to obtain admin privileges on Windows systems. And my conference is entitled Testing UAC on Windows 10. I will firstly explain the user controls, then I will show you some attacks in order to bypass that mechanism, and finally I will show you another way to bypass the user account controls. My name is Ernesto Fernandez. I'm a computer engineer. I have a master's degree in cybersecurity, and here you have a few links if you are interested in knowing a little bit more about my profile or ask whatever question you may think of. First of all, let's focus on what the user account control is and how it works. I'm sure that when you use Windows and when you run an application as an administrator, this things happens. You start the application and this is what happens. Well, this window is asking us for admin permission. This is the user account control, and this is how it basically works. It is a mechanism to prevent malware execution in Windows environments without user permission. And it is done through the so-called consent prompt. Here there are three examples. The color shows us the level of confidence that Windows has in terms of the certificate of the process we want to run. If we don't belong to the administration group, we will be asked administration credentials. The user account control was initially designed for Windows Vista, where there was just one security level. In 7, 8, and 10, there are 4 security levels. In Windows Vista, the only security level was the so-called notify. And what does this level do? Well, it means that any application run with admin permission will require consent from the user, regardless of the certificate. The next level, the default level, well, it's pretty similar, but several applications which are in a so-called safe directory and have activated the auto level characteristic activated, and their portfolios won't need it. The next level is exactly the same as the former one, and when an application needs permission, the glare, the brightness in the screen will dim down. So now let's focus on the different attacks that we can use in order to bypass the user account controls, the so-called bypass and UAC attacks. What we want to do is execute an application without the with administrator rights, but without the user knowing. We need several requirements. These are the three main ones. We will need a vulnerable auto-elevate process. We will also need that the user to belong to the administrator's group. This is a final condition, and the UAC security level does not have to be set to always notify level. This is a condition that can be bypassed in some cases. Now I will give you some examples from the last 2 years, new developments related to this kind of attacks. Let's begin with Enigma. Enigma used a programmable task in order to bypass the user account control. Another example is from a Dutch researcher who used the process tpmlniet.exe in order to bypass the user account control. The next one is Tyrannid's Lair by James Forsyth, who used the token impersonation in Windows systems. Another example by the guise of break-in malware used their variables in Windows. Another example by Enigma that took advantage the API of the cell in order to bypass the user account control without requiring further files. Another one is from Shitao, a Russian researcher who overlapped the user interface privilege isolation of Windows system through a trolled process. Another example is fast security, which would use the .NET interface in order to bypass the user account control. Finally, there is this UAC me repository that contains all the methods I've so quickly mentioned. I took a look at it a couple of days ago, and there are currently 44 methods to bypass the user account control. Most of these methods are already patched, but there are about 15 methods that are still usable. There are multiple methods like this. If we try to categorize them, we can create 6 main categories. The most famous one was developed in 2009 by using a DDL hijacking process in order to bypass user account control. What is DDL hijacking? Well, we want a process to upload a malicious DLL under our control instead of the original one. And here we can tell 7 different categories in terms of attacks and DLL hijacking. The most popular one was iFile operation. And with this process, we want to deceive the iFile operation object so that when we invoke it, we do so with the maximum level of integrity. So this is done by an injection of processes, as you can see on the top left, and then it will look like a trustworthy process. Once we do that, we will invoke this with a maximum level of integrity, and we will copy the DLL to a location under our control. We would finally execute the auto-elevated process that would upload our DLL. Another example is the WSA method that would use the Windows Update standalone installer. The first step is to compress the DLL into a CAB file. Then we would extract the DLL into any location in the disk, in particular the one we were interested in. Then we would our DLL would be the one to be used. This has been totally patched, and the extract functionality has been suppressed from Windows. The next example is about bypassing the user interface privilege isolation, which prevents lower integrity processes from sending messages to higher integrity processes. We want to do this by injecting an iFile operation within an auto-elevated process executed with the highest level of integrity. The first step, therefore, is to inject the iFile operation within a Windows trusted certificate process that will allow us to copy 2 elements, a process that is going to be run with a high integrity level and a malicious DLL. Both elements will be copied inside a secure path, as Microsoft calls it. What is a secure path? Well, all the paths that are within the route slash Windows and a few others. Once they are copied, the process is going to be executed with the highest level of integrity, and then the DLL hijacking process will start. Then the DLL is going to be run, invocating an auto-elevate process to finally invoke the process we are interested in. I hope this can be seen more clearly in the diagram. The next example talks about abusing the environment variable expansions in Windows. Why? Because several auto-elevate processes upload DLLs from routes with environment variables. If an attacker modifies an environment variable and the path works on a variable under its control, the DLL will be finally uploaded. Another example for this kind of attacks is the so-called race condition attack. Here we try to run a process that creates or uploads DLLs that may be overwritten so that we overwrite the last one of all. I'm going to show you the concept test by Enigma with this screen up with a temporary file on which several DLLs were copied and also a process. This is all run with admin rights and maximum integrity level. The temporary file would run the application with admin rights. So it would upload the same DLLs in order. So this guy found out that he could overwrite the last one. He would bypass the user account controls. One of the most recent attacks is the one using COM handlers. What is that? Well, a COM handler specifies a COM object by its CLSID key, from which the process associated with it will load a DLL. So if an attacker modifies one of these COM handlers to an address under its control, our DLL will be loaded instead of the original one. Here you can see the different variables that would need to be changed in the register and what the process looks like. Another pretty new hijack or attack is the so-called NTFS repass point. In Windows, this would be a symbolic link or a delicious point. So we would compress the malicious DLL into a cap file as in the WUSA file before. Then we would create a WSA.exe file that will allow us to extract our DLL to any location in the hard disk without using anything else. So finally, when the DLL is copied, we will run the auto-elevate process that will load our DLL instead of the original one. Now, leaving the hijacking attacks behind, we are now going to talk about the abuse of several COM interfaces. A COM interface defines a set of methods that a COM object can invoke. The problem appears when several interfaces provide rights without user consent. So what happens if the hijacker finds in one of these COM interfaces providing rights, a process that allows for a command to be run, they can redirect the process to a method under their control. And this is quite a simple process. One of the methods that we used to use in the past is the application compatibility exploiting. In Windows, this allows us to run processes that were conceived for former Windows systems into current Windows system via the shim files. The shim files establishes several modifications on a particular process. In our case, an attacker in the past, for example, an attacker could create a malicious shim file in order to invoke a process, and they would apply this shim file into an auto-elevate application that would activate the shim file, and the process would be executed in an auto-elevate manner. This attack has a CVE number, which means that the international community and Microsoft has a deprecated category. Now, going back to the so-called shell API method, we can say that several auto-elevate applications use these shell APIs to execute its own commands or invoke several applications. How are we going to attack it? Well, by modifying the registry and executing a command that we are interested in. We will execute two categories: attacks modifying an environmental variable, or manipulate a registry variable. Here are two examples. If we focus on the first part of this variable, which is used to execute a command, you can see that the environment variable is system root. If an attacker modifies this variable and directs it to a directory under his control, they will be able to trigger the process they want. If they modified the second part, the variable wouldn't point at mmc.exe but to a different thing. Executing that command with the shell API, and the user account control wouldn't have been a barrier to it. One of the most intelligent, complicated, and recent methods is the so-called token impersonation abuse in Windows systems. In Windows, a token is the mechanism that Microsoft has in order to manage the rights attached to the different processes. This is the diagram developed by James Forshaw. First of all, we have to check the rights of the application with high-integrity processes, for example, mmc.exe. By modifying the permissions, they would get the query-limited information access right. So what he achieved with this was impersonate and duplicate rights that would allow him to copy the token and apply all the necessary changes so that it would be impersonated in the relevant process. So he wouldn't be able to modify the original token, but he would modify the copied token. So once the token was impersonated, the process would earn administrator rights immediately. This is now the only method that's not susceptible to the always notify security level. That's very interesting indeed. My final example has to do with the use of the user interface and the file search function. They are looking for a particular process. They are running it as an administrator, and the user account control hasn't been any barrier. Now, regarding malware or cyber criminality, this is irrelevant. Now, let's focus on the most interesting part for everybody here, which has to do with the development of a new method for bypassing the user account control. I based the deferred operation method but then I applied it to new elements, as I'm going to show you right now. The first thing I did was to verify the applications that had an auto-elevate characteristic, and I used the strings command for it. The result is quite a high number of applications, so I ruled out all the applications for which there was a known method for bypassing the user account control. Then I ran all the processes and checked the execution flow for each of them. So now we are going to see it more visually now. Thank you. The first thing we're going to do is take a look at the manifest of the auto-elevate process in order to check that this is a process that grants rights. Here we can see that the auto-elevate feature is activated, so we are not interested. So now with Process Monitor, we configure several filters and we try to see the execution flow of the process. DCCW.exe. It pops up, we close it immediately because it's of no interest to us, and we look at the execution process. There are several URLs, and at some point it looks for the directory where DCCW.exe is executed. So what can we do at this point? We can create this directory and see if it uses any file that would be useful for an attack. So now I have preloaded and created several directories and other things to run tests. I copy the directory we're interested in, and we execute DCCW.exe again, but we will start with process monitoring first. We execute it, we close it again, and as we see, it runs again. Here we can see that it uploaded satisfactorily, but on top of the directory hasn't created the directory with AMD64, etc. What can we do about it? Well, we can create a new directory and verify whether we can use some kind of load, DLL, or other elements, as in the former example. We've copied a directory with the path we want. Then we relaunch Process Monitor to see the running process from DCCW.exe. At this point, we can see that it wasn't run satisfactorily. Why? Because if we take a look at the error message, it says that it was trying to find this file, heavyplus.dll, which means that they need to upload a DLL from this route. So what can we do about it? We can provide our own DLL in order to check if this runs with admin privileges or rights or not. I have previously created a DLL with these characteristics, as in the former example. We're going to copy it. As you can see, here is the DLL. I don't want you to focus on the other directories. I will explain why in a few minutes. First of all, we copy the directories. We relaunch process monitoring in case it was helpful, and then we execute DCCW.exe. It looks that we've achieved nothing. We have this code, this error code that at first sight doesn't look very useful. And if we look at the execution flow, we can see the directory we've created, the route we've created, and GD plus our malicious DLL. Now, If we look further down, we can't see anything that can help us verify what has happened exactly. I was a bit lost in the beginning regarding, well, I didn't know what had happened, but when I was researching several fora and blogs, I came up with the solution. dccw.exe needs to upload several functions from the original file. What can we do about this? We can verify the functions with gdplus.dll, and a tool I'm going to use is PEView. You can also use IDAP Pro or other tools. We upload it and we go back to the export address table. And here we're going to find all the functions that are exported. It's quite a high number, 635 functions exported by gplus.dll. One option is to copy them all and don't leave anyone behind, but there are applications for doing this automatically. However, this is quite an inefficient solution. So what can we do about it? Well, dccw.exe, I'm sure it doesn't require 635 functions from this DLL. So what can we do? Let's look at this table file. If we now go back to the imported table and the DLL we are interested in, we will see that it only needs a very small number of gdi+.dll functions, only 15. So we've gone down from 635 functions to 15 only. So the reduction in volume of our final DLL is going to be very significant. Now we have another problem. We have to redirect the execution flow to the original DLL. Here in Process Monitor, the directory name is here as I am highlighting, and it shows us that the etc is quite a long number and apparently random. But if we take a closer look at this number, I don't know if you can see it, it is actually the same one as the build version of the Windows system we are running our concept test in. So if we redirect all this flow to the original DLL, that is within /window /Windows NX /directory /this name, it can be only executed on the Windows systems whose version of the bill is the same one as the one we have in our concept test. That is not efficient. So what can we do? We can redirect this to a DLL that is common to all Windows 10 systems. So I did a little bit of research myself. So this directory contained a DLL with the same name that we're interested in. After analyzing it with several tools, I realized that the functions were similar, were the same, and they were enough to redirect the flow to our DLL file. So this is what we are going to do. As in the other cases, I have directory systems that I have copied previously, so I'm going to replace what I previously copied. If we execute dccw.exe, now we've obtained a command terminal. If you look at the top here, we have administration rights. This allows that we can perform an attack bypassing the user account control. So now we're going to take a look at the process that enables us to automatize all this huge task. I showed you before that I was also copying other 3 directories with similar names. Why? Because dccw.exe is going to upload the gdplus.dll in every execution time, and it's going to change the route every time. So this route is going to be unpredictable. I'm sure somebody will be able to do it, but the most efficient solution would be to copy the entire file route, all these folders, and include our malicious DLL on top of them.
Vamos a borrar lo copiado en.
Let's delete a few things here that I've copied it before in order to remove all the traces.
Pues, a ver, ahora, no. Las diapositivas no cargan. A ver. A ver. Ahora, bueno, me vale. Aquí, bueno, explico un poco todo lo que os he estado contando.
So, here's a little bit what I've been explaining, how the copying process works, how the vulnerability is discovered, how the hijacking attack is performed, etc. So now, focusing more on the concept test. Our goal is to perform an interoperable concept test. We've seen that all the execution flows will be directed to the directory that I've shown you and the route that I've showed you. So this will prevent this from running on Windows 7 because this route isn't present in these systems. At the same time, we also wanted to execute this in 32-bit versions and in 64-bit versions. So we decided to compile all the binary files, DLLs, the final concept test, and the 32-bit process one. Why? Because they allow us to run this kind of applications too. This will entail changes in the directory routes in the future, but we will find out more in a minute. When it comes to the malicious DLL, I've talked about the redirection and how we want to export some functions, etc. In this case, we are going to compress it into base 64 and encode it in our concept code. The compression method used will prevent this from running on Windows 7. The next step, once the concept test is executed, is performing several initial checks. We are going to check the build version, we're going to check if we have administrative rights, we're going to check if the compromised user belongs to the administrator's group, and we're going to check the UAC security level as well. Why? Because we don't want to be unsuccessful in our concept test. We're going to create all the temporary elements I've talked about in the same directory where the concept test is going to be run. First of all, we will create the dccw.exe.local folder, and on that in that folder we will copy all the directories that will match with the one that is highlighted on the screen. As you can see, this is the first change produced by the compilation of the test concept as a 32-bit binary. So this shouldn't cause any problems in theory. Then, after all these directories have been created and copied, we're going to copy our malicious DLL, and then we are going to run the critical part of the exploit that is going to enable us to invoke the COM object process with our highest integrity level. In the case of C++, I'm going to use a method called masquerade PEB, or the modification of the process environment block in English. Why do we do this, and how are we going to do it? Well, We want the process environment block in our process to look like an application with a trustworthy certificate from Windows or Microsoft, so that to the eyes of PSAPI, it looks like one of the applications. Why? Because PSAPI tells the COM object we are invoking the process that is being invoked. If we change the process to make it look like one of these processes, we will be able to run the object with the highest integrity level. With Metasploit, we will perform a process injection. We will inject a DLL into a Microsoft-signed application. In this example, we have notepad.exe, and we will run it on this process. Once we've invoked the iFile operation object, we will be able to copy the entire row of files we've created, the dccw.xw.local, and with the routes that you can see on the screen. With the 64-bit system, we have the second change we've discussed. It's going to be copied to the route that you can see at the bottom of the screen. We would finally execute the process dccw.exe, and our DLL will be executed with administration rights. Then we would remove all traces, all temporary files, so that future executions aren't affected.
This is the diagram of the concept test we've done in order for it to be clearer and easier to understand. And now we go into the section that everybody wants to hear about, and that is the proof of concept thing, to see whether everything works. But before this, we're going to go over a series of requirements in order to be able to run the concept trial or test where in a satisfactory manner in the C++, and in the other thing, we're going to make sure that this will be Windows 8 or 10, and the user's source control is the maximal level, and finally for the user to belong to the group of administrators, and the target option must match the processor architecture of the victim. And now going into
Vale. Primero vamos a ejecutar la.
So we're going to run the
En C++. No, espera.
The concept test. Let's see. Wait a second.
Como vamos a ver, pues se va a ejecutar de forma bastante rápida.
So all the different steps that I've explained to you are going to be analyzed, all the temporary thing and everything else. So we execute, and then we have some commands with the permission or authorization of the administrators. So we were able to skip the UAC. This with the permission of the administrator. So in a satisfactory way, we've been able to attack. In the case of Metasploit, what we do is first of all start this. I'm going to load a little script that's going to automate the whole thing. In the case of Windows, what I did was to create a backdoor so that it will create this meterpreter thing. And if we go into this session, we'll see, we'll see what user we are. So, standard user, if we go into this command in order to scale up privilege, we see that 4 attempts have been made, and we haven't been able to get permission from the administrator. So it means that the UAC prevented us from doing it. And going back to our module, we'll check whether options are the right ones. This is so. Looks like it. If we execute exploit, then we'll see how all the processes that I've been telling you of are executed. And if everything goes as expected, we're going to go into the interpreter session. We go to get system, and with the same technique we were able to, if we check what user we are, we see that we are the user with more privilege in the system. And going back to the presentation. Oops, again. Crashed. There we go. Here I left some videos that you can view later. But wrapping up my presentation, I'm going to the opinion of Microsoft. What does Microsoft think about this sort of attack in order to skip or bypass UAC? Well, they say that a weak point that allows to skip this UAC is something that cannot be considered vulnerability because it's not considered as a security mechanism. But it also says that UAC is a fundamental component of Microsoft's overall security vision. So as we see, there's a clear confusion here. And as regards what I think about this, my opinions and the conclusions on the achievements, I can say that as regards conclusions, skipping UAC is not a hard thing to do, and I believe that Microsoft should start considering these attacks as a reality, that they're here to stay in order to protect users, because the patches that come up with each new version are not enough. Finally, I'd like to say that nowadays the only solution, the most effective one, is to create 2 different users in the Windows system with different administrators permits with a lower level perhaps, and always use this last one. And finally, as regards achievement, a whole new method has been developed in order to skip or to bypass this UAC in all Windows 10 versions. And the module's been included in the popular Metasploit framework. And to finally end, and if you want to know more or learn more about the project that I've developed and the attacks in order to bypass these UACs, I left here a repository of the project, and I've also included the paper and left a couple of links on Metasploit module, and I also wanted to leave a link there to the this project, UAC project, for those of you who are interested in this sort of attacks, because I'm sure you think that it is very interesting. By the way, I will also upload this, have it in LinkedIn. And finally, thank you so much for your attention. Thank you very much indeed. And if you have any questions, I'll be happy to answer them, or at least try to. Okay, nobody There's nobody. Well, Ernesto, thank you so much. Thank you very much. A big round of applause.